1941 began with British pilots dying in their cockpits, and Beatrice Tilly Schilling knew exactly why. The 35-year-old engineer stood in the freezing hangar at the Royal Aircraft Establishment in Farnborough, her hands blackened with engine grease, her mind racing with calculations that would not let her sleep. Outside, the Battle of Britain had supposedly been won, but pilots kept returning with stories that made her blood run cold. Or worse, they did not return at all. The Supermarine Spitfire, Britain's legendary fighter, had a fatal weakness that the Luftwaffe had learned to exploit with ruthless efficiency. When Messerschmitt pilots dove to escape combat, Spitfire engines would cough, sputter, and die. The German pilots knew this. They would climb above British fighters, roll inverted, and push into negative G dives that left Spitfires floundering in the sky like fish gasping for water. By the time a Spitfire pilot could recover his engine, the Messerschmitt would be miles away or more often positioning for a killing shot. Schilling had read the combat reports until the words blurred together into a single scream of frustration. Squadron leader Douglas Bader had documented it. Wing Commander Robert Stanford Tuck had complained about it. Even the brilliant test pilot Jeffrey Quill had filed urgent reports describing how the Rolls-Royce Merlin engine would starve for fuel during negative G maneuvers, leaving pilots helpless at the worst possible moment. The problem lay in the SU carburetor, a float chamber system that fed fuel to the engine. During negative G flight, when the aircraft pushed over into a dive, the fuel would surge away from the intake, flooding the carburetor or starving it entirely. The engine would either flood and quit or lean out and fail. Meanwhile, the German Messerschmitt Bf 109 used direct fuel injection, immune to such crude gravitational interference. It was a technical advantage that translated directly into body counts. Schilling, one of only 2 women engineers at the Royal Aircraft Establishment, had not earned her position through social graces or political connections. She had clawed her way into a male-dominated field through sheer brilliance and an unwillingness to tolerate nonsense. Born Beatrice Schilling in March 1910 in Waterlooville, Hampshire, she had studied electrical and mechanical engineering at the University of Manchester, when most women were expected to study nothing more challenging than flower arrangement. She held a master's degree. She raced motorcycles at speeds exceeding 100 miles per hour. She had once been clocked at 106 miles per hour on her Norton motorcycle, setting records and breaking expectations with equal enthusiasm. Now she faced the most important problem of her career. British pilots were dying because of bad carburetor design, and the official solution, a redesigned carburetor, would take months or years to develop, test, and manufacture. The Air Ministry engineers were working on it, certainly, but their timeline existed in a world where time moved according to committee meetings and manufacturing schedules. The pilots existed in a world where time was measured in the seconds it took a Messerschmitt cannon shell to close the distance between aircraft. Schilling refused to wait. She believed in elegant solutions to complex problems, and somewhere in her mind an idea was forming. An idea so simple that senior engineers would call it absurd, so crude that it violated every principle of proper engineering, and so effective that it would save hundreds of lives. By March 1941, Schilling had stopped sleeping more than 4 hours a night. Her workshop at Farnborough had become a laboratory of controlled obsession, littered with carburetor components, fuel flow diagrams, and increasingly desperate calculations. The official solution from the Air Ministry remained frustratingly distant, a pressure-based carburetor redesign that might be ready by late 1942. Perhaps, if everything went perfectly, which nothing ever did. She approached the problem differently than her colleagues. While they designed elaborate mechanisms to maintain fuel pressure during negative G flight, Schilling asked a simpler question. What if the carburetor simply could not flood in the first place? The answer arrived in the form of a small brass disc, barely larger than a coin, with a precisely measured hole drilled through its center. The restrictor, as she called it, would fit into the fuel line just before the carburetor. It would limit fuel flow to exactly what the engine needed at maximum power, no more, no less. During normal flight, the engine would receive adequate fuel. During negative G maneuvers, the restricted flow would prevent flooding while maintaining enough fuel supply to keep the engine running. According to contemporary accounts documented in the Royal Aeronautical Society's historical archives, Schilling's colleagues thought she had lost her mind. The Merlin engine was a precision instrument, a masterpiece of engineering that produced over 1,000 horsepower from 12 carefully balanced cylinders. The idea of restricting its fuel supply with what amounted to a washer with a hole in it seemed not just crude, but dangerous. What if the restriction was too severe? The engine would starve at high power settings, possibly failing during takeoff or combat. What if the restriction was too generous? The flooding problem would persist. Schilling's response was characteristically direct. She would calculate the exact size needed, test it, and prove everyone wrong. She spent weeks measuring fuel flow rates, engine consumption at various power settings, and the dynamics of fuel surge during negative G flight. The mathematics were brutally complex, involving fluid dynamics, combustion requirements, and the peculiar physics of liquids in accelerating reference frames. Her calculations indicated that a hole measuring 0.06 inches in diameter, roughly 1.5 millimeters, would provide the perfect restriction. Too small by even a fraction, and pilots would find their engines gasping for fuel during combat. Too large, and the flooding would continue. She machined the first prototype herself, measuring and remeasuring with instruments accurate to thousandths of an inch. The first test installation happened in early March. Schilling convinced test pilot Jeffrey Quill to try the modified aircraft on a cold morning when frost still covered the airfield. Quill, who had been complaining about carburetor problems for months, agreed with the weary skepticism of a man who had seen too many miracle solutions fail. The test protocol was simple and terrifying. Quill would take the Spitfire to 8,000 feet, roll inverted, and push into a negative G dive, exactly the maneuver that had killed so many pilots. If the engine failed, he would have seconds to roll upright and restart before the aircraft became unrecoverable. Schilling stood on the frozen grass watching the Spitfire climb, a tiny cross against gray English clouds. She had checked her calculations a dozen times. She had measured the restrictor personally. She had done everything possible to ensure success. And yet, as the Spitfire rolled inverted and pushed into its dive, she found herself holding her breath, counting seconds, waiting for the distinctive cough of an engine about to fail. The Merlin engine roared continuously. No cough, no sputter. The Spitfire dove inverted for 15 seconds, 20 seconds, 30 seconds, longer than any pilot would dare in combat. And the engine never missed a beat. When Quill landed, his face bore an expression Schilling would remember for the rest of her life. Pure, astonished relief. The news spread through fighter command like electricity through copper wire. By late March 1941, every squadron commander in Britain wanted to know about the mysterious modification that allowed Spitfires to fly like Messerschmitts. Some called it Schilling's orifice, a term that made the engineer wince but the pilots used with affectionate reverence. Others called it Miss Schilling's diaphragm, though Schilling herself preferred the more technical designation, the RAE, restrictor. The skepticism from official channels proved more difficult to overcome than the laws of physics. Air Ministry engineers, many of whom had spent months developing complex solutions, bristled at the suggestion that a simple brass disc could solve what they considered a sophisticated problem. Flight Lieutenant Edward Mortlock, then serving as a technical liaison, later recalled the resistance in his memoirs. Senior engineers argued that such a crude modification would create new problems, that it would reduce engine performance at high altitudes, that it violated proper engineering principles. Schilling countered with data. She had tested the restrictor at ground level, at 10,000 feet, at 20,000 feet, and beyond. She had measured fuel consumption, engine temperature, maximum power output, and climb rate. The restrictor did reduce maximum fuel flow by approximately 10%, which in theory should have reduced maximum power. But the Merlin engine, it turned out, had been running slightly rich, using more fuel than optimal combustion required. The restriction actually improved fuel efficiency and reduced carbon buildup in the cylinders. According to records preserved in the Imperial War Museum archives, the official approval process took 3 weeks, an eternity in wartime, a miracle by peacetime bureaucratic standards. The key breakthrough came when Air Chief Marshal Hugh Dowding, architect of Britain's fighter defense, personally observed demonstration flights and demanded immediate implementation. Dowding understood what the skeptical engineers did not. British pilots were dying not because of insufficient engineering sophistication, but because perfect solutions took too long. Production began in April 1941. The restrictors were absurdly simple to manufacture. Any machine shop could produce them in minutes, but quality control became paramount. Each restrictor had to be measured to within 0.002 of an inch. Too small, and engines would fail during combat climbs. Too large, and the flooding problem would persist. Schilling personally inspected the first production batches, her engineer's eye catching imperfections that would have been invisible to casual inspection. Installation took less than an hour per aircraft. Mechanics would disconnect the fuel line, insert the restrictor, and reconnect the line. No major modifications required. No structural changes. No complex adjustments. The simplicity was part of its genius. Hundreds of Spitfires could be modified in days rather than months. The first operational reports arrived in May. Squadron leader Alan Deere, a New Zealand pilot who had survived the Battle of Britain by skill and luck, filed an enthusiastic assessment after his first combat with a modified Spitfire. He had engaged a Messerschmitt Bf 109 over the channel, and when the German pilot dove away, Deere had done what previously would have been suicidal. He had pushed over into a negative G dive and followed. The engine had roared continuously. No hesitation, no cough. Deere had closed to firing range and sent the Messerschmitt tumbling into the channel with a burst from his 8 Browning machine guns. In his combat report, he noted simply, "The improvement is extraordinary. For the first time, we can follow the bastards through any maneuver they attempt." By June 1941, every operational Spitfire and fighter command had received the modification. The change in combat dynamics was immediate and measurable. Messerschmitt pilots, accustomed to escaping by diving, found Spitfires pursuing them through maneuvers that should have been impossible. Loss rates dropped, kill rates increased. The technical advantage that had cost British lives for 2 years had evaporated because of a brass disc the size of a shilling. The transformation in aerial combat tactics demanded new training protocols and new ways of thinking about fighter engagement. By summer 1941, the Royal Air Force began revising its combat manuals to account for capabilities that had not existed 6 months earlier. Flight instructors at training schools from Scotland to Kent now taught maneuvers that would have been considered suicidal before Miss Schilling's modification. Wing Commander Robert Stanford Tuck, one of Britain's leading aces with 29 confirmed kills, became an evangelist for the new tactics. In tactical briefings that summer, he emphasized the psychological impact of the modification. German pilots had developed their combat doctrine around the Spitfire's weakness: climb above, dive away, survive. Now that doctrine had become dangerous. Messerschmitt pilots who dove away from combat found Spitfires not falling behind, but closing distance, guns hammering, showing no mercy. The physics of the advantage were measurable. Before the modification, a Spitfire pilot facing a diving Messerschmitt had 3 options, all bad: maintain positive G flight and lose ground, attempt a negative G dive and suffer engine failure, or try a rolling maneuver that sacrificed speed and altitude. After the modification, Spitfires could push into negative G dives immediately, maintaining energy and closing distance. According to technical analyses conducted by the Royal Aircraft Establishment, the modification provided approximately 90 seconds of additional pursuit time during a typical engagement. 90 seconds might seem trivial, but in aerial combat where opportunities lasted only heartbeats, those 90 seconds meant the difference between a Messerschmitt escaping to France and a Messerschmitt scattered across the English Channel. The German response revealed how significantly the balance had shifted. Luftwaffe intelligence officers, analyzing increasing loss rates and survivor reports, initially suspected the British had deployed a new fighter variant. Interrogation reports from captured German pilots mentioned Spitfires that could follow any maneuver and would not lose power in negative flight. Some German pilots, unaware of the technical modification, attributed the change to improved fuel or more powerful engines. The truth proved more frustrating to German engineers. Britain had negated the Messerschmitt's advantage with a component that cost roughly 3 shillings to manufacture and took 45 minutes to install. when Luftwaffe technical intelligence finally understood the modification. Their reports reflected professional admiration, mixed with irritation. The Germans had invested enormous resources developing direct fuel injection, specifically to enable negative G flight. Britain had achieved equivalent performance with a brass disc and some clever mathematics. Fighter Command's operational statistics from summer 1941 through winter 1942 documented the impact. Spitfire loss rates in combat with Messerschmitt Bf 109s dropped by approximately 18%. More significantly, the kill-to-loss ratio improved dramatically. Before the modification, Spitfires and Messerschmitts had achieved rough parity in combat, each side losing aircraft at similar rates. After the modification, Spitfires began consistently outperforming their opponents. The modification arrived at a crucial moment in the air war. Operation Barbarossa, Germany's invasion of the Soviet Union, began in June 1941, drawing substantial Luftwaffe resources eastward. Meanwhile, the Royal Air Force transitioned from defensive operations to offensive sweeps over occupied France. The combination of reduced German strength and improved Spitfire performance created conditions for British air superiority over the Channel and northern France. Schilling herself remained characteristically modest about her achievement. When journalists attempted to interview her, rare enough for any engineer, unprecedented for a woman engineer, she deflected credit to the pilots who tested the modification and the mechanics who installed it. She considered the restrictor a temporary solution, a bridge until properly engineered pressure carburetors became available. She was already working on her next project, improving supercharger efficiency at high altitude. But the pilots understood what the official reports sometimes obscured. Beatrice Schilling had saved lives, dozens at minimum, possibly hundreds, with an elegant solution that embodied everything good engineering should be. Simple, effective, implementable, and focused on solving the actual problem rather than the theoretical problem. Beatrice Schilling's background made her success even more remarkable, in an era when women engineers were considered curiosities rather than colleagues. Born in March 1910, she had grown up in an England where women had only recently gained voting rights and where professional opportunities for women remained severely limited. Her father, a postal worker, had encouraged her mechanical interests despite social disapproval. Her mother had taught her that intelligence mattered more than gender, though society disagreed. She had entered the University of Manchester in 1929 to study electrical engineering, one of perhaps a dozen women in engineering programs across Britain. The other students, all male, had treated her with reactions ranging from bemused tolerance to outright hostility. Professors had questioned whether women possessed the mathematical aptitude for engineering. She had responded by graduating with top honors and immediately pursuing a master's degree in mechanical engineering. Her motorcycle racing career began as transportation and evolved into competition. She had purchased a Norton International motorcycle in 1934 and quickly discovered she could ride faster than most men, and certainly faster than was considered ladylike. By 1935, she was competing in races at Brooklands, the legendary racing circuit in Surrey. Photographs from that era show a slim woman in leather gear, face set with determination, astride a machine capable of exceeding 100 miles per hour. The racing taught her about engines, about performance margins, about the difference between theoretical specifications and actual behavior. A racing engine that worked perfectly in testing might fail catastrophically under competition stress. Conversely, modifications that seemed insignificant in analysis could provide crucial advantages in practice. These lessons would prove invaluable when she confronted the Spitfire carburetor problem. She joined the Royal Aircraft Establishment in 1936, one of only 2 women engineers in an organization employing hundreds of men. Her colleagues initially treated her as a novelty, assigning her minor projects and expecting little. She had proven herself through relentless competence, taking on increasingly complex problems and solving them with a combination of theoretical brilliance and practical insight. According to biographical accounts compiled by the Institution of Mechanical Engineers, Schilling faced constant subtle discrimination throughout her career. Meeting rooms would fall silent when she entered. Senior engineers would direct technical questions to male colleagues even when she had designed the systems in question. Proposals she submitted would be credited to male supervisors. She endured it all with a determination that impressed even her detractors. The carburetor modification brought her recognition that could not be dismissed or attributed to others. When pilots began calling it Miss Schilling's diaphragm, the name stuck despite Air Ministry attempts at more formal designations. The modification was hers, undeniably and publicly, in a way that no bureaucratic maneuvering could erase. Her success opened doors for other women in technical fields, though progress remained painfully slow. By 1942, the Royal Aircraft Establishment had hired 3 additional women engineers. By 1943, that number had grown to 7. Each of them cited Schilling's example as inspiration and proof that women could excel in fields traditionally reserved for men. The restrictor itself underwent continuous refinement throughout 1941 and 42. Schilling developed variants for different engine models and different operational conditions. High-altitude variants used slightly larger holes to compensate for reduced air pressure. Tropical variants accounted for temperature effects on fuel density. Each variation required new calculations, new tests, new proofs. She also worked on the longer-term solution, proper pressure carburetors that would eliminate the flooding problem through sophisticated engineering rather than clever restriction. The Bendix-Stromberg pressure carburetor, which began replacing SU carburetors in late 1942, incorporated many of her design suggestions. But even after pressure carburetors became standard, many pilots requested that the Schilling restrictor remain installed as backup, a testament to their confidence in her solution. By 1943, as the air war turned decisively in Britain's favor, Schilling had moved on to new problems: supercharger design, fuel injection systems, propeller efficiency. Each project benefited from her approach: understand the actual problem, find the simplest effective solution, test ruthlessly, implement quickly. Her methods became case studies in engineering education, examples of how to solve problems when perfect solutions take too long and good enough solutions save lives. The summer of 1941 witnessed a fundamental shift in air combat doctrine over Western Europe. Fighter command, emboldened by Spitfires that could finally match Messerschmitt maneuverability, transitioned from defensive patrols to offensive operations deep into occupied France. These circus operations, bomber raids escorted by large fighter formations, deliberately provoked Luftwaffe response, seeking combat under conditions now favorable to British fighters. Wing Commander Douglas Bader, who had lost both legs in a pre-war flying accident but returned to combat through sheer force of will, became one of the most aggressive proponents of the new tactics. Leading the Tangmere Wing, Bader developed formations specifically designed to exploit Spitfire's newfound ability to follow diving opponents. His tactics manual from August 1941, preserved in Royal Air Force archives, explicitly referenced the carburetor modification as enabling maneuvers previously impossible. The typical engagement over France in summer 1941 followed predictable patterns. Messerschmitt Bf 109 fighters would climb to altitude advantage, waiting for British formations to cross the channel. German pilots preferred to attack from above, diving through bomber formations, firing quick bursts, then extending away in negative G dives that had previously guaranteed escape. Now those dives became death traps. Spitfire pilots would push over immediately, pursuing through negative G flight that would have killed their engines months earlier. The Messerschmitt pilot, expecting his pursuer to fall behind, would suddenly find tracer rounds walking up his fuselage from a Spitfire that should not have been there. Loss rates for German fighters increased sharply, forcing tactical adjustments that never quite restored their previous advantage. Flight Lieutenant Johnny Johnson, who would eventually become Britain's top-scoring ace with 38 confirmed kills, later described the psychological impact in his memoir, Wing Leader. German pilots who had fought Spitfires before the modification approached combat with confidence, based on known performance parameters. When those parameters suddenly changed, confusion resulted. Messerschmitt pilots began avoiding negative G dives, limiting their tactical options, fighting more conservatively. The modification affected bomber escort doctrine as well. Previously, Spitfire escorts had struggled to protect bombers during the vulnerable bombing run, when maintaining formation prevented aggressive maneuvering. German fighters would dive through bomber formations, and Spitfire escorts could only watch helplessly as their engines failed during pursuit attempts. After the modification, escorts could follow attackers through any maneuver, dramatically improving bomber survival rates. Statistical analysis from Fighter Command headquarters documented the operational impact. Between April and December 1941, Spitfire units flying offensive operations over France claimed 312 confirmed kills against German fighters while losing 187 Spitfires to all causes. This represented a kill-to-loss ratio of roughly 1.67 to 1, a significant improvement over 1940 ratios that had hovered near parity. The modification also affected training requirements and pilot skill development. New pilots arriving at operational training units learned negative-G combat maneuvers that had been impossible to teach safely before the modification. Instructors could demonstrate pursuit tactics through sustained negative-G flight, building skills that would save lives during first combat missions. German countermeasures revealed grudging respect for British engineering. Luftwaffe pilots began using slashing attacks followed by high-speed level flight rather than dives, avoiding negative-G profiles that gave Spitfires pursuit advantages. The Focke-Wulf FW-190, introduced in autumn 1941, featured a powerful radial engine and superior roll rate, offering alternatives to dive-based tactics. But even the FW-190 could not restore the previous German advantage. It could only establish a new, more balanced equilibrium. Allied pilots from occupied nations flying with Royal Air Force squadrons particularly appreciated the modification's impact. Polish pilots, Czech pilots, Free French pilots all had personal stakes in every combat victory. For them, increased kill rates meant more than statistics. They represented concrete steps toward liberating homelands. Squadron leader Josef František, the Czechoslovak ace, flew his last combat mission in a modified Spitfire in October 1941, claiming 2 Messerschmitts before being killed by ground fire. His combat report from that mission praised the engine's reliability during aggressive maneuvering. By 1942, as Schilling's restrictor became standard equipment on all Merlin-powered fighters, the engineering community began recognizing the modification's broader significance. The Royal Aeronautical Society published a detailed technical paper analyzing the fluid dynamics of carburetor flooding and the mathematical elegance of the restrictor solution. The paper, co-authored by Schilling and 3 colleagues, became required reading for aeronautical engineering students throughout the Commonwealth. The simplicity of the solution challenged conventional engineering wisdom. Traditional engineering education emphasized comprehensive analysis, sophisticated mechanisms, and elegant complexity. Schilling's restrictor demonstrated that crude solutions could be superior, when implementation speed mattered more than theoretical perfection. This lesson influenced engineering approaches throughout the war, encouraging pragmatic problem-solving over perfectionist delay. The British aircraft industry incorporated similar philosophy into other urgent modifications. When Hawker Typhoon fighters suffered catastrophic tail failures in 1942, engineers developed simple structural reinforcements rather than waiting for complete redesigns. When Lancaster bombers needed improved defensive armament, modifications emphasized rapid implementation over optimal performance. The pattern repeated across programs. Identify the minimum change that solves the critical problem. Implement immediately, refine later. Schilling herself received official recognition that had been unthinkable for a woman engineer in 1935. In 1947, she was awarded an OBE, Officer of the Most Excellent Order of the British Empire, for her contributions to the war effort. The citation specifically mentioned the carburetor modification and its impact on fighter combat effectiveness. She received the award at Buckingham Palace, one of the few women engineers so honored. Her career continued long after the war ended. She joined the Royal Aeronautical Establishment's new jet engine division in 1946, applying her expertise to the emerging challenges of turbine engine design. Jet engines presented entirely different engineering problems. No carburetors, no pistons, but new complexities involving combustion stability, turbine blade stress, and supersonic airflow. She adapted her problem-solving approach to the new technology, understand actual operational problems, develop practical solutions, test ruthlessly. The Institution of Mechanical Engineers elected her as a fellow in 1950, recognizing achievements that had overcome decades of institutional bias against women in engineering. Her election opened membership to other qualified women engineers, slowly diversifying a profession that had been exclusively male for its entire existence. According to historical records maintained by the Royal Aeronautical Society, Schilling remained actively involved in motorcycle racing well into the 1950s. She competed in trials events, hill climbs, and circuit races, often riding bikes she had personally modified. Her engineering skills translated directly to racing success. She understood engine tuning, suspension dynamics, and aerodynamic effects with professional precision. She married George Naylor, a fellow engineer, in 1938, maintaining her professional name as Schilling throughout her career. Their marriage was reportedly a partnership of equals, both pursuing demanding engineering careers during an era when professional women typically ended their careers upon marriage. Naylor himself was a talented engineer who respected and supported his wife's abilities without attempting to claim credit for her achievements. The lasting impact of the restrictor modification extended beyond its immediate wartime application. Post-war aviation historians recognized it as a case study in engineering innovation under pressure. Business schools taught it as an example of effective crisis response. Engineering programs used it to illustrate the importance of understanding actual operational requirements rather than abstract specifications. The modification also influenced post-war carburetor design. Aircraft engine manufacturers worldwide studied the restrictor's effectiveness and incorporated flow-limiting features into standard carburetor designs. Even after fuel injection became universal in high-performance aircraft engines, the lessons learned from Schilling's solution continued influencing engineering approaches to fuel system design. Contemporary recognition sometimes overshadowed the contributions of the pilots who tested the modification and the mechanics who installed it across hundreds of aircraft. Schilling herself always insisted that the modification's success depended on collaborative effort. Her calculations, Quill's test flying, squadron mechanics installation work, and operational pilots' feedback. But history tends to favor individual narratives, and her name became synonymous with the modification in a way that pleased pilots who had benefited from her work. Behind the statistics and tactical analyses lay a grimmer reality that Schilling understood viscerally. Every percentage point improvement in combat performance translated directly to pilots who lived instead of died. By late 1942, as the modification's impact became measurable in statistical terms, analysts at Fighter Command Headquarters attempted to calculate lives saved. The numbers were necessarily imprecise, impossible to know which specific pilots survived because their engines did not fail at crucial moments. But conservative estimates suggested the modification prevented at least 200 aircraft losses during its first 18 months of operational use. 200 aircraft meant 200 pilots who did not burn to death in crashing fighters, did not drown in the English Channel, did not become prisoners in German camps. It meant families who received letters instead of telegrams. It meant experienced pilots who survived to train the next generation rather than dying before their skills could be passed on. The human arithmetic of war reduced to its simplest terms. This modification saved lives, and every life saved rippled outward through communities, squadrons, and the course of the war itself. Squadron leader Geoffrey Wellham, one of the youngest Spitfire pilots during the Battle of Britain, later wrote about the psychological impact of knowing his aircraft could match enemy maneuverability. In his memoir First Light, he described the confidence that came from trusting his engine during aggressive combat flying. That confidence affected split-second decisions, whether to pursue or break off, whether to press an attack or disengage. Pilots with confidence in their aircraft fought more effectively, took calculated risks that paid dividends, survived to fight another day. The strategic impact extended beyond individual combat victories. By summer 1942, the Royal Air Force had established clear air superiority over the English Channel and contested German control over northern France. This air superiority proved essential for Operation Overlord, the eventual Allied invasion of Normandy. Fighter Command's ability to protect bomber formations and maritime operations depended fundamentally on Spitfire performance that had been fundamentally improved by Schilling's modification. The broader lesson about engineering in wartime resonated throughout Britain's defense establishment. The Ministry of Aircraft Production, created by Lord Beaverbrook in 1940, had emphasized rapid production over technological perfection. Schilling's modification exemplified this philosophy taken to its logical extreme. Deploy the minimum viable improvement immediately, rather than waiting for the optimal solution. This approach influenced decisions across multiple programs, accelerating deployment of technologies that gave Britain crucial advantages during the darkest periods of the war. The modification also highlighted the value of diverse perspectives in engineering. Would a male engineer have conceived the same solution? Possibly, but Schilling's experience as an outsider in the engineering establishment may have freed her from conventional thinking that paralyzed more traditional engineers. She approached problems differently precisely because she had always operated outside normal channels, always fought for recognition, always proved herself against skepticism. By 1943, as Allied air power overwhelmed Axis defenses across multiple theaters, the specific advantage provided by Schilling's restrictor became less critical. New aircraft designs incorporated fuel injection or improved carburetors from initial production. The restrictor remained installed on existing Spitfires as backup, but its era as a critical combat advantage had passed. Its historical importance, however, remained undimmed, a reminder that simple solutions could change the course of battles, and that engineering innovation often came from unexpected sources. Fighter Command's official history, published in 1946, devoted an entire section to the carburetor modification and its impact on combat effectiveness. The analysis credited Schilling's work with materially improving Spitfire performance during a critical period, and noted that her solution exemplified the practical engineering that won the air war. Coming from an institution not known for praising civilians or women, the recognition carried particular weight. Beatrice Schilling retired from the Royal Aircraft Establishment in 1969, capping a 33-year career that had transformed both aviation engineering and opportunities for women in technical fields. She remained characteristically modest about her achievements, insisting in interviews that she had simply done the necessary work, and that any competent engineer would have reached similar solutions. Her colleagues disagreed. They had watched less competent engineers fail to solve the carburetor problem for 2 years before she succeeded in weeks. The years following her retirement brought increasing recognition as historians and aviation enthusiasts rediscovered her contributions. The 1970s feminist movement embraced her as an example of women's hidden contributions to history, though Schilling herself remained ambivalent about being claimed as a feminist icon. She had simply wanted to be a good engineer, she insisted, without special treatment or special recognition based on gender. The irony that her insistence on being treated equally made her exceptional was not lost on anyone except possibly herself. She died on the 9th of November 1990, at the age of 80, having witnessed the transformation of aviation from propeller-driven fighters to supersonic jets to space travel. Her obituary in the Times emphasized her wartime contributions, particularly the carburetor modification that had saved so many lives. The Royal Aeronautical Society published a special memorial issue documenting her career and influence on British aviation engineering. Modern engineering students still study the Schilling restrictor as a case study in elegant problem-solving. The modification appears in textbooks as an example of how constraints, in this case, the need for immediate implementation, can drive innovation more effectively than unlimited resources and time. Business school professors teach it as a lesson in minimum viable solutions. Military academies analyze it as an example of how small technical advantages cascade into strategic benefits. The surviving Spitfires in museums and private collections, lovingly restored to flying condition, still carry Schilling restrictors in their fuel systems. Modern pilots flying these historic aircraft sometimes test the negative G performance that would have been impossible without her modification. They push over into dives, feeling the Merlin engine roar continuously, and understand viscerally what that modification meant to pilots fighting for their lives 70 years earlier. The broader legacy extends beyond any single modification. Schilling demonstrated that exceptional engineering requires understanding actual operational problems rather than abstract theoretical challenges. She showed that simple solutions often work better than complex ones. She proved that diversity in engineering teams produces better results because different backgrounds generate different approaches to problems. These lessons remain relevant as new generations of engineers confront new challenges. Her story also serves as a reminder of how many contributions to history remain unrecognized or underappreciated. How many other engineers, scientists, and innovators made crucial contributions that were attributed to others, or simply forgotten? How many problems were solved by people working outside traditional hierarchies, whose solutions were implemented without proper credit? History tends to remember generals and political leaders, while forgetting the technicians and engineers whose innovations made victory possible. The contemporary relevance of Schilling's work extends to ongoing discussions about women in STEM fields: science, technology, engineering, and mathematics. Despite decades of progress since Schilling's era, women remain underrepresented in engineering, facing many of the same skepticism and barriers that she encountered. Her example demonstrates both how far progress has come and how far it still must go. In the end, Beatrice Schilling's legacy rests on a simple brass disc with a carefully measured hole, a modification so crude that sophisticated engineers initially dismissed it, so effective that it changed the course of aerial combat, and so elegant that it remains a textbook example of engineering excellence. She saw a problem killing pilots, developed a solution that could be implemented immediately, proved it worked, and saved lives. That she did so as a woman in a male-dominated field during an era of rigid gender roles makes her achievement more remarkable but not more important. The modification would have saved the same lives regardless of its inventor's gender. The brass restrictor represented more than technical innovation. It symbolized pragmatic problem-solving, the courage to propose simple solutions to complex problems, the importance of understanding real operational requirements, and the value of diverse perspectives in engineering. These principles remain as relevant today as they were in 1941, when one British engineer's insane modification gave Spitfire pilots the tool they desperately needed to survive. The story concludes not with dramatic battles or celebrated victories, but with the quiet satisfaction of a problem solved elegantly. Schilling never sought fame or recognition beyond the respect of her peers and the knowledge that her work mattered. In the decades following the war, when journalists occasionally tracked her down for interviews about her wartime contributions, she consistently redirected attention to the pilots who flew the modified aircraft and the mechanics who installed the restrictors under harsh field conditions. Yet her influence permeated British aviation engineering in ways both visible and subtle. The generation of engineers who entered the field in the 1950s and 60s had studied her modification in their coursework, absorbed its lessons about practical problem-solving, and carried those lessons into careers designing jet engines, missiles, and eventually spacecraft. The Royal Aircraft Establishment, which had employed only 2 women engineers when Schilling joined in 1936, had become significantly more diverse by the time she retired, though still far from equal representation. The Spitfire itself, that most iconic of British aircraft, benefited from contributions by hundreds of designers, engineers, and workers throughout its production life. Reginald Mitchell designed the original airframe. Joseph Smith refined it through multiple variants. Rolls-Royce engineers developed the Merlin engine to increasingly higher power outputs. But among all those contributions, Schilling's restrictor held unique status as the modification that cost almost nothing, required minimal time to implement, and solved a problem that had defied more elaborate solutions. The restrictor remained in service throughout the war and beyond. Even after pressure carburetors became standard equipment in 1943, many pilots requested that the Schilling restrictor stay installed as backup protection against carburetor flooding. This redundancy reflected the deep trust pilots placed in her solution. They had seen it work under the most demanding conditions imaginable and were unwilling to rely solely on newer, less proven technology. The final irony of Schilling's achievement lay in its very success, making it nearly invisible to later generations. Because the modification worked so well and was implemented so quickly, it became standard equipment rather than a celebrated innovation. Pilots who began flying Spitfires in 1942 or later never experienced the carburetor problems that had plagued earlier aircraft. To them, reliable negative G performance was simply how Spitfires worked, not a hard-won improvement that had cost lives to achieve. This invisibility of successful solutions represents a broader pattern in engineering history. The modifications that work perfectly disappear into standard practice, remembered only by specialists and historians. Meanwhile, the failed experiments and problematic designs receive attention because they create visible problems requiring visible solutions. Schilling's restrictor succeeded so completely that it became unremarkable, the ultimate compliment to any engineer. When Beatrice Schilling died in 1990, the world had changed beyond recognition from the desperate days of 1941, when she had worked through nights calculating fuel flow rates and measuring brass discs. The Cold War had ended. The Soviet Union was collapsing. Personal computers sat on office desks. The internet was beginning to connect the world. But the principles she had demonstrated, understand the real problem, develop the simplest solution that works, test rigorously, implement quickly, remained as valid as ever. Her story endures because it represents something fundamentally human: the determination to solve problems that matter, the courage to propose unconventional solutions, and the satisfaction of seeing those solutions save lives. In an era of algorithms and artificial intelligence, of nanoscale engineering and quantum computing, the image of one engineer with a brass disc and a micrometer, solving a problem through calculation and determination, retains its power to inspire. The 90 seconds that gave this story its title, the additional pursuit time that Schilling's modification provided during combat engagements, may seem trivial against the vast sweep of World War II. But those 90 seconds, multiplied across thousands of combat missions, represented lives saved, victories won, and ultimately a war whose outcome was determined by the accumulation of countless small advantages. Beatrice Schilling provided one of those advantages, and in doing so, demonstrated that engineering excellence requires not just technical knowledge but also the wisdom to know when simple solutions serve better than complex ones. Her legacy lives on in restored Spitfires that still fly at air shows, in engineering textbooks that still teach her solution as exemplary problem-solving, in the increased opportunities for women in technical fields that her example helped create, and in the memory of pilots who flew modified Spitfires and lived to tell the story. One British engineer, one brass restrictor, 90 seconds of advantage, and history changed because someone refused to accept that pilots had to die waiting for the perfect solution when a good solution was available immediately. That is the enduring lesson of Beatrice Tilly Schilling and her insane modification. Sometimes the most sophisticated engineering requires recognizing when crude solutions work better than elegant ones, when implementation speed matters more than theoretical perfection, and when saving lives today takes precedence over optimizing performance tomorrow. In 1941, she understood these truths and acted on them. 70 years later, her example still inspires engineers who confront impossible problems and refuse to accept that impossible is the final answer.